Now here's what we're going to do. I'll introduce a few words for you, right? If a line passes through a circle, right? If it passes through and it just slices across, something like this. In fact, we can all draw this. Okay? If a line slices through a circle, it's called a secant. Secant. S-E-C-A-N-T. If it slices through and it intersects the circumference twice. Okay? Now, what I'm going to do is I want to think about what happens if the secant, rather than intersecting twice, if I move it lower and lower and lower until such a time that it intersects only once. It then gets a special name. What's it called? A tangent, right? We're going to draw one eventually, right? We'll get there in a second. So we're going to think about what happens as this secant becomes closer and closer to a tangent. To understand what I'm looking at, I'm thinking in particular about if I connect these two radii here, okay? Let's do a bit of labeling here. Let's do a bit of labeling. It's conventional to call the center of the circle O. And then we've got these 2 points on the circumference where our secant intersects with our circle, okay? So I'm going to call those 2 points of intersection, I'm going to call them P and Q. And so that we can also refer to our secant in a meaningful way, I'm going to call the ends of the secant A and B. Okay, so our secant AB cuts the circle at P and Q. So far, so good? Okay, one last piece. Even though all of this is lines, what I'm actually interested in here, and the result I'm going to go towards, is an angle. Okay, so I'm going to label this angle up here. I'm just going to call it theta. Okay, call it theta. And now let's get to work on this diagram. Okay, what I'm going to get towards is, what is this angle OPA over here? That's what I'm going to try and find out. And it doesn't take too much work to get there. Okay. Before we get to that angle, that's the angle outside the triangle, the exterior angle. So it makes sense to think about the interior angles. Okay. Now remember, we drew OP and OQ and they are radii, so that means that they are equal to each other. So in here we've got an isosceles triangle. You agree with that? Okay. So if I can find out what each of these are, then I can find out what OPA, or APO rather, is. Okay? So if I just do the angle sum of a triangle in here, noticing that it's isosceles, I can say OPQ, right, plus this angle here, which is the same as OPQ. Okay? Those two angles, if I add them to theta, that's the whole triangle, right? That's the whole triangle. So they add up to? They add up to 180, right? Angle sum of a triangle. Okay, don't worry too much about the reason at the moment. I just want to establish this result so you can see it. Okay. So now it doesn't take too much to tidy this up. I've got two lots of OPQ on the left-hand side, two of them. And if I drag over that theta to the other side, I've got 180 minus theta. Agreed? So therefore, I can just divide both sides by 2, and that gives me this. Okay, so now I have a value for this interior angle. What I'm really after is the exterior angle. Yeah? Okay, so how would I work that out? I can take that exterior angle, add it to my interior angle, and because they're on a straight line, they should equal 180. Good. Okay, so now let's just tidy this up. APO plus 90 minus theta on 2, half theta. Okay, and if I make APO the subject, what do I get over here on the right-hand side after I even roll out? 180, I'll take away 90, which leaves me with 90, right? And then I will, because I want to add theta on 2 to both sides to get rid of it, over on the left, I'll have 90 degrees plus theta on 2. Does that make sense? So I'm now going to, that's the angle I was after, I'm going to pop that onto my diagram. 90 degrees plus theta on 2. And because of the symmetry of this thing, you've also got it over here, 90 degrees plus theta on 2. You could rehearse exactly the same thing, but instead of A's and P's, you'd have B's and Q's. Okay? Okay, now we are going to think about what happens to this secant as it gets closer and closer to a tangent. Okay? So for example, let's draw the same diagram now, but imagine if we drop down AB, that secant, if we dropped it down lower. Okay, so for example, something like this. Okay? If AB is still a secant, but it is further away from the center of the circle, okay, I've still got much the same configuration. Okay, here are my points of intersection. Okay, how would you describe the difference between scenario 1 and scenario 2? How would you articulate it? Apart from the fact that the secant's gone further away, what other things do you notice? Yeah. Yeah, good. So before I had this really wide angle here, it was obtuse, right? And now, as you said, Eric, it's getting smaller. So much smaller, in fact, that for this, I've got an acute angle in there, okay? So this angle theta is getting smaller. It's getting smaller, okay? But all of the things we said before are still true. They're still true. This angle over here, exterior, is still 90 plus theta on 2, right? In terms of structure, nothing has changed, right? It's still the same. Okay, so now, here's what we're going to do. We're going to take the limit of this situation as P and Q come together, because that's what they're doing, right? You see they're getting closer and closer together, okay? In fact, we can make them coincide, right? Here's the center. If this moves all the way down so that you have a tangent, right? By the way, tangent, there's a Latin base to that word. We get another word in our English language from the same root as tangent. Does anyone know what word we get from it? Tangible, which means something you can touch, right? A tangent is just touching the circle rather than slicing through it, okay? It's a tangent. Now, where are P and Q in this diagram? They're both right there. They're both sitting on top of each other, yeah? So there's P and Q, right? I still got A, B over here. Okay, now remember you told me going from scenario 1 to 2, theta went from wide to narrow. Where's theta? Here. Now, this is a bit tricky, and this is why limits are a tricky idea. Theta is right in there, right? It's POQ. A way you could say it is that theta is 0. I mean, that's kind of meaningless because there's no angle there, but if there were an angle, it'd be 0. Okay? But I still haven't changed like the arrangement of this situation, right? So this angle here, APO, right? It's 90 degrees plus theta on 2. But what's theta?
0.
It's 0. So what's this angle?
90.
It even looks like that, doesn't it? Okay. Not only can you argue it from the fact that it has to be just 90 because theta has gone towards 0, okay? But we can also say, hey, look, these two angles here we established are the same angle. It's a symmetrical diagram, right? The only way you can have two symmetrical diagrams, two symmetrical angles, I should say, that are sitting on a straight line is that both of them, of course, must be 90 degrees. Do you agree with that? Does that make sense? Okay, so therefore my conclusion out of this is the property that gets named out of this. In this situation here, the tangent, which we've drawn as AB, the tangent is perpendicular. Perpendicular to what? How would you describe this line here? It's the radius to the radius, but it's not just any radius. A circle has an infinite number of radii. Here are some, right, which have nothing to do with my actual tangent, right? So they're not just perpendicular to the radius, they're perpendicular to the radius at the point of contact. That point which we've called P, or Q if you like.